Section 2 of Unit 2 is on asymptotes, one-sided limits, and limits at infinity. We're going to kind of skip through this part. You're not going to do this. I kind of did it for you already. But numerically, which means using your calculator or table, we're going to find the following limits. First one is limit as x approaches 0 from the left of 1 over x. We know just by looking at this that we have a discontinuity at 0. Okay, I can't plug in 0 into the function 1 over x because the function's undefined at 0. Okay, but we can look at what our function's approaching as we're approaching 0. Okay, see what's happening to our function as we get really, really close to 0. We know we're not going to find what it is exactly at 0 because it doesn't exist at 0. Let's see what it's approaching. So 0 from the left, that's numbers really, really close to 0 that are negative. So negative 0.1, negative 0.01, negative 0.0001. As I plug in these values, 1 divided by those numbers approaching 0 are getting really, really big. Negative 10, negative 100, and I keep multiplying by a factor of 10 as I get closer. Well, what's going to happen if I keep adding zeros and I keep approaching 0 from the left? It's going to get bigger and bigger and bigger, and it's going to approach negative infinity. Now, if I looked at the limit as x approached 0 from the right of 1 over x, this would become positive, and all these would become positive. So as we get closer and closer to 0, this number on the bottom gets really, really, really small, infinitesimally small. And that number divided by a number that's extremely small turns out to be something that's extremely big. And this time it would be in the positive direction. That gives us what our function looks like, 1 over x. As we get close to 0, to the right of 0, we're approaching positive infinity. We're up here. And then we shoot down here. As we approach 0 from the left, we're going to be approaching negative infinity. Okay? So, kind of using this, we're going to say stuff. If k is a positive number and our denominator is approaching 0, so k is some positive number and our denominator is approaching 0 from the left. Well, a number that's approaching 0 from the left would be like negative 0.0001 or something like that. Any constant divided by something that's infinitesimally small is something really, really big. In this situation, since the infinitely small thing is negative, this would be negative. And like we can take our calculator and kind of show that. We could take some positive constant. It doesn't even have to be a whole number. We can even take some decimal, 0.6, and divide it by something really, really small. We'll get something really, really big. Okay? We have this positive constant, and we're dividing by something really, really small, but it's something really, really small and positive, then we're going to get something really, really big and positive. If I make this constant negative, in negative k, we're dividing by something that's really, really close to 0, really, really small, but it's negative. Well, a negative divided by a negative, you know, is a positive. This is also a positive. And if this is negative, and this is something extremely small, but it's positive, this would be something really, really big, but in the negative direction. Okay, it's important also to know what it means to be 0 from the right. That's like a number that's just positive, but really, really small. Everybody understand that these concepts. Anything divided by something really infinitesimally small is really, really big. Okay, so that's important to know. Just a quick definition of asymptotes. If the limit as x approaches c from the left of f of x and the limit as x approaches c from the right of f of x is equal to infinity or negative infinity, then we say that x equals c is an asymptote. So some people asked last class, how do we know if this is a jump or is an asymptote if you have a non-removable discontinuity? Well, here's the answer. We look at the limit as we approach those values. If it's a jump, we are going to be approaching a value. We won't be approaching infinity. If it's an asymptote, we will be approaching infinity as we're approaching that value. Questions? All right, so let me show you how I do some of these problems. Anybody need that for another second? Evaluate the limits. Limit as x approaches -1 from the left, -1 over x plus 1. And then from the right, and then we're going to look at it in general. We know this function is not defined at -1, okay? But we want to see what is our function approaching as we're approaching -1. So, what I like to do first is just give myself an example of what -1 from the left is. So what's -1 from the left? Give me an example of a number that's approaching -1 from the left, Ms. Glazer. A numerical example, like a number. Yep, get closer though. So closer to -1, but from the left. What do you think, Ms. Gilman? Mr. Head? Yeah. Ms. Gilman? Yeah. -1.1, -1.01, something like that. Sorry for putting you guys on the spot. Okay. So, to find this limit, I have -1, and I'm going to plug in this as it looks like here, in for x. Similar to how we were finding limits, the easy limits, where we could just plug in our values. Well, this is kind of like -1 divided by something that's really, really close to -1, but just a little bit smaller, like that. Okay? If I add these two numbers together, well, first I'll have the -1 up top. But if I add these two numbers together, what is my result? Yes, -0.001. So that is a number approaching 0 from the left. A number that is just a little bit negative. Thank you. Okay, I'm not even going to look at this so much as look at this. A number that it's a little bit more negative than -1, like -1.01. If I add that to 1, I'm going to be approaching 0, but from the left. I'm going to have a number that's just a little bit negative. It's infinitesimally small, but it's negative. So what's a negative divided by something infinitesimally small but negative? Positive infinity. Okay, second one. Negative 1 from the right. That's like negative 0.9 repeated. I have negative 1 divided by, I'm going to plug in this. Negative 1 from the right plus 1. Knowing that this is negative 0.9 repeating, negative 0.9 repeating plus 1 is some number that's getting really, really close to 0, but it's positive. Some number getting really, really close to 0 divided into any constant is going to be something really big. The question is the direction. It'll be in the negative direction this time. Okay, and if you wanted to show that using your numerical number, you could have done the same. Okay, but I honestly don't like to do this because I don't have my calculator and sometimes I get confused, and I'd rather just kind of do that using this example. So this is positive infinity, this is negative infinity. They're not approaching the same thing. We say this definitely does not exist. We have an asymptote. X equals negative 1 is a asymptote. Okay? Questions? Do the first two of these. And just know that it's the same process. And if you have something that's infinitesimally small and you're squaring it, well, it's still going to be infinitesimally small. It'll just be positive. Look up on the board when you're done. Check your answers. Oh, jeez. No, number less than 4. From the left, to the left of 4. I always assume I'm wrong. That's a good question. Everybody understand what I did?
Why is negative 5 over
Any constant, anything divided by something extremely small is going to be something extremely big. So -5 divided by 0.00000001 is going to be something huge. Okay? Now, if we did it correct, we would have gotten it's -5 over some number approaching 0 from the left, but that's squared. A infinitesimally small negative number squared is still going to be really, really, really small, just positive. Take that number, divide it into -5, we're going to be approaching negative infinity. And it's the same thing over here, only we'd be approaching 0 from the right, something extremely small. Squaring that, it's still something extremely small from the right that's positive, be negative. Now for this one, you could say that the limit as x approaches 4 in general of this is negative infinity. Or you could say it still does not exist. If we go back to our limit definition, the definition of a limit was our function had to approach some specific value L, okay, for the limit to exist. And it had to approach that L from the left, and it had to approach that L from the right. Well, infinity is not a value L. Infinity is something we can never touch. It's just we continue to get bigger and bigger and bigger. So the AP testers accept both this and this as answers to a question like this. Okay? This is technically right, but it's also technically wrong if you go strictly by the definition. But you say from the left and from the right, the function's approaching negative infinity. Doesn't mean it's meeting up or anything. There is an asymptote. Okay? Let's do a couple others. I want you guys to try this one. This one, and then this one down here if you can see it. Okay, try it by yourself. I'm not going to wait too long because we have to continue to move on, but I'll show you what I would do up on the board, okay? First thing I would do to help me out is write a number that's approaching -3 from the right. A lot of people like to think that it's a number like -3.001 because you think like numerically 3.001 is bigger than 3, but that's not the case. See if you got that one right. Try the second one. I really didn't care that this was -1 from the right because it's just a constant. It'll just be approaching -1 from the right. I can consider that a constant in the numerator. It's the denominator that I really care about, especially when that denominator is approaching 0 and is an extremely small number. Questions about how I did this one? I need you guys to try these first and see if you get the same thing. So try that bottom left one first. See if we can get the same thing. I'll tell you, it's either positive infinity or negative infinity. The question is which one. That's the tough part. All these homework problems, you're just going to want to be like, ugh, I'm just going to put infinity. But we need to figure out if it's approaching infinity in a positive direction or negative direction. This is supposed to be 2. I'm sorry. You just did negative 3, you would have gotten just a value. My bad. Positive 2. Whatever. 2 from the left minus 1 is like 1. 2 from the left minus 2 is like 0 from the left. That gives you positive infinity. You got the same answer when you plugged in negative 3, then you did it wrong, yeah. Then you would have just gotten negative 4 over negative 5, which is 4/5. You don't have to do this in factor if you plugged in 2. So you just gotten 2 squared plus 2 times 2 minus 3. In the bottom, meaning this is 2 from the left. The bottom you have 2 from the left squared plus 2 from the left minus 6. Okay? So that's like 1.999. I square that. I'm going to get close to 4, but from the left. Something close to 4 from the left and close to 2 from the left is something close to 6 from the left. 6 from the left minus 6 is something that's very, very small, but negative. Very, very close to 0, but negative. In the top, you add 4 plus 4 minus 3, which is 5. Yeah, I'll just keep that. You add 5 over 0 from the left. Wait. Should have gotten the same thing. 8, 5. Oh, sorry. Negative. Okay. Questions? Tricky. Okay. Your calculator can help you work through a couple of these problems, but you have to do these problems without your calculator. Okay. You can plug in an exact number like 1.999 into this and see what you get. A big number that's positive or a big number that's negative. All right. These one-sided limits involve trig sometimes. go ahead and write a little bit of a unit circle, coordinate plane, and label your extremes. Okay, with trig functions, when we're dealing with the unit circle, 0's over here at 1, 0. And we go around our circle counterclockwise to get positive values. Okay? If I went to the right clockwise, that's going in a negative direction. This is going in a positive direction. This is going in a negative direction. So, if I'm approaching 0 from the left, so I have a number that's a little bit less than 0, which way am I coming from? From here into there, from here into there. From the first quadrant or the fourth quadrant? Fourth quadrant. A number that's less than 0 is over here. So this is 0 from the left in the fourth quadrant. This would be 0 from the right. Well, pi over 2. If I'm going pi over 2 from the right, am I in the second quadrant or the first quadrant? Pi over 2 from the right would be in the second quadrant. Right here we would say this is pi over 2 from the right. And this would be pi over 2 from the left. You go ahead and label the from the lefts and from the rights at pi and 3 pi over 2. This is a number a little bit less than pi. This is a number a little bit bigger than pi. A little bit less than 3 pi over 2. A little bit bigger than 3 pi over 2. Okay? Now, this is going to help us, and our mnemonic, awesome students take calculus, is going to help us. Telling us which trig functions are positive in which areas. Okay? I'll show you why that helps us. We're trying to find the limit as x approaches 0 from the left of 1 over the sine of x. Well, I know that the sine of 0 is just 0. But with trig, it's a little difficult just to assume that the sine of some number approaching 0 from the left is also equal to 0 from the left. Okay, we have to check. We check our coordinate plane. So, 0 from the left down here. As I'm approaching 0 from the left, my sine values are going to be approaching 0, but since I'm in the fourth quadrant, the sine values are negative. So I say that is also 0 from the left. So 1 over the sine of x, as x approaches 0 from the left, is like 1 over the sine of a number approaching 0 from the left, which is something extremely big in the negative direction. Okay, and this would be obviously the opposite. It would be like 1 over the sine of 0 from the right. 0 from the right's up here. It's in the first quadrant. My trig function, all my trig functions are positive in the first quadrant. So that's why I know that's like 1 over something approaching 0 from the right, which is also positive infinity. Okay? Now you guys do something with cosine of pi over 2 from the left. See how that looks. See where you are when you're at pi over 2 from the left. See what your cosine values are going to be. What are they approaching? Okay. Anybody confident with their answer? They would like to explain to everybody what they did. Yes. Shannon, go ahead.
The first one is coming from the always, or the first quadrant where everything's always positive.
Yep.
And so it would be 1 over something positive, so you know it's going to be positive infinity.
Exactly.
And then...
Now, it's not over something positive, it's something really, really small, but positive. Infinitesimally small, but something positive. Because we're coming from the left of pi over 2 in the first quadrant. See how it kind of flipped up on us here. And then the second one?
The second one is going to be in the second quadrant where only sine's positive, so cosine is going to be negative, so it's going to be 1 over something really, really small that's negative, and that's negative.
Beautiful. Everybody see her thought process through that. Okay. Try cotangent. First, you got to figure out what the cotangent is, right? So this is telling you that we're going to get some form of infinity. The question is, what is it? Mr. Braddock, did you get this one? Yes. Sine, as we're approaching pi from the left is right here. Sine is positive from the left of pi. So this is actually approaching 0 from the right. It's a number very, very close to 0, but it's positive. The cosine of pi is -1. Okay, we could say this is approaching -1 from the left as well if we wanted to, but no need. The combination of these two things is negative infinity. Okay? And a little tricky. You need to practice them. Okay? When you practice them, you'll improve on them. Let's move on. Limits at infinity. If we looked at the same function 1 over x, and instead of approaching 0, we approached infinity. So this reads the limit as x approaches infinity of 1 over x. Okay, this is the infinity symbol. Everybody read that? Ms. Forkey, can you read that? Okay. So as my x's get bigger and bigger and bigger, what are my function values doing? Getting smaller. So as I continue to plug in bigger and bigger values into my denominator, what is this function approaching? 0 is correct. Notice the graph of my function. As my x's get bigger and bigger and bigger, my function is trending towards 0. This is what we call a horizontal asymptote. Now, just quickly, just so we can wrap our brains around it, if k is some constant and our denominator is approaching some huge value, okay, it doesn't matter what k is. It could be a huge value as well. But this infinity is going to overwhelm it eventually, and this entire thing is going to trend towards 0. And if it was approaching negative infinity, it'd be the same thing. It would be approaching 0. Now we can say that it's approaching 0 from the right or from the left, but it's really not from the right and the left anymore. We're talking about y values, and that's like above and below. So approaching 0 from up here, approaching 0 from down there. So we don't even do that. We just say it's approaching 0. Okay? Now, it's easier when we're talking about limits at infinity rather than limits as your denominator is approaching 0. So we have these guidelines. First guideline is the highest power term of a function is the most influential in determining a limit at infinity. And I'll give you an example. Okay. As x approaches infinity, the only thing that really is going to matter is this. Okay, you might think, oh, that doesn't really make sense because these things are like big. Yeah, well, when x is small, yeah, they'll matter. But as I plug in bigger and bigger values, and we're talking like, 10 to the power of some value, like 10 to the 100, this stuff grows so much slower than an x to the 4th that it ends up just being like just little fluff that will barely move where my function's going. You think, well, I mean, they're big, and we have an x squared and an x cubed. Even still, just having that one extra multiple of x, that will be the influencing term. And really, our function in this example of that will really just be like the same thing as this. And this will trend towards infinity. Okay, if the degree of my numerator is greater than the degree of my denominator, my function will be approaching infinity. Here, my degree of my numerator, the biggest degree is the 4th power. It is bigger than anything in my denominator. Hence, for this first problem, f of x, the limit as f of x approaches infinity, That's infinity. If the degree of my denominator is greater than the degree of my numerator, f of x will approach 0. An example. Let's find the limit as x approaches infinity of, x squared plus 1000x, all divided by 4x cubed. Let's just say that's just 4x cubed. Since 4x cubed is the most influential, as x is approaching infinity, this will grow faster than this. And since this is growing faster than this, my function, my denominator, will continue to get bigger and bigger than my numerator. Since it's going to get bigger and bigger and bigger, my numerator won't go that fast. We'll be approaching 0. Finally, really quick, as we approach infinity, if I have the same degree terms, and it doesn't matter what else I have, my function will be approaching just the coefficients of those most influential terms. This is determining what my function is going to divided by that. Okay, those are easier than the ones as our denominator is approaching 0. There's one maybe tricky one dealing with square roots, and we'll go over it. But if you know this, you'll be fine. Thank you for staying after the bell.